swing around the sun and starts heading toward Earth, that will confirm that this is intelligent life and intelligently controlled. What do we do then?
You know, it's a threat to the future of humanity. It could be a black swan event with a low probability.
I just wanna see you one last time. To see you one last time.
The 3I Atlas comet is currently visiting our solar system. On December 19th, it will come closest to the Earth. I've noticed a few differences between 3I Atlas and normal comets. Hyperbolic orbit, non-gravitational acceleration, a tail facing towards the sun, and abnormal color temperature. I strongly believe that we are witnessing extraterrestrial life coming to us. But if they chose to visit us, do they plan to observe us or attack us? Well,
just trying to keep you safe in the storm and in the rain. Don't you?
Hey, the song's fantastic. Who made the song? I did. Here are 5 main features that I think distinguish 3I Atlas from normal comets. 1. The hyperbolic orbit. 3I Atlas follows a really hyperbolic path. In casual terms, it doesn't orbit the sun at all. Due to its insanely fast speed, it is deflected by the sun's gravity much less, with eccentricity greater than 6. I'm gonna explain this word later on. Most asteroids near our solar system don't behave like this. Number 2 is source of the non-gravitational acceleration. Aside from the acceleration due to the sun's gravity, we observe another component of acceleration seemingly out of nowhere, and its magnitude is almost identical to the acceleration caused by the sun in the opposite direction. What is causing this external force? We can explain.
I just wanna see you one last time. To see you one last time.
Number 3. There's a tail from 3I Atlas facing towards the sun. Usually for a comet that's coming towards the sun, its tail points away from it due to the solar wind. But the observation shows another tail pointing inward and is unusually bright. This is again evidence that something else is controlling it.
Won't you fly with me tonight? Don't care, don't.
Number 4. It glows with blue light before it gets close to the sun. By color temperature, a yellowish white hue implies 6,000 Kelvin, like the sun. But 3I Atlas is glowing a blue hue, placing the temperature above 10,000 Kelvin before it gets close to the sun, suggesting that something else is at play.
I'll be there to save you one last time. To save you one last. Won't you?
Number 5. The trajectory is astonishingly close to the direction of Jupiter. This non-gravitational acceleration mentioned earlier is altering the direction of 3I Atlas' path to Jupiter. In March 2026, it will enter Jupiter's Hill sphere, a region where Jupiter's gravity is stronger than the Sun's. Simulations have shown that the probability of this happening is 1 in 260,000. Again, strong evidence that something is controlling it. How the hell are there this many coincidences? 3I Atlas is an extraterrestrial spaceship.
Won't you fly with me tonight? Don't care, don't.
He used his invented vector calculus to describe the orbit of planets and asteroids, really worthy of being Newton. 真牛逼. Today, I'm going to quantum entangle with Newton across time, put his soul into my body, and use his vector calculus ideas to derive a model for the shape of a planet's orbit and protect us from near-Earth asteroids. Let's get started. If r and v lie on the xy plane, L points purely in the z direction. When r is perpendicular to v, the particle can be viewed as moving in uniform circular motion, where r is a fixed radius. Using the law of gravitation, we get that the top speed is the square root of gm over r. This v0 will be the top initial speed. Any faster than that, and the planet will not orbit around the sun. The derivative of L using the product rule will be the derivative of r cross mv, which is v cross mv plus r cross ma. The cross product of two vectors is 0, and f, as we saw earlier, is parallel to r, so both the v cross v term and the r cross f term vanish. The derivative of angular momentum is 0, so angular momentum is conserved. We'll now convert to polar coordinates by x equals r cosine of theta and y equals r sine of theta. Here the r and the theta are both functions of t, the time. Differentiating the position unit vector, we get this expression above. We get this expression where theta is the unit vector in the angular direction. We now define the kinetic energy as 1/2 m times the top speed squared, and potential energy, which is negative gmm over r. When r is perpendicular to v, only the direction part exists, so the kinetic energy, k0, will be 1/2 m times the square root of gm over r, all squared, which is gmm over 2r. The total energy, E0, is the sum of the kinetic energy and the potential energy, so gmm over 2r minus gmm over r, so we get negative gmm over 2r. Our force field, F, is conservative, which means its line integral across a closed path is 0, so the total energy is conserved. The work done from point A to point B is computed with a line integral shown here, where C is our orbit curve from the starting point to the final point. Reparametrizing with time, we get the second equation, which is equal to the negative change in potential energy U of r. Since the gravitational force is conservative, we can write the force field as the negative gradient of the potential energy. From the second equation, we can write the net force equals m times the derivative of velocity, so we get this expression here. Now notice that the velocity dot its derivative can be written as 1/2 times the derivative of the velocity magnitude squared. So we can express L2 as this expression here. Now using FTC part 2, this equals the change in 1/2 mv squared, or the kinetic energy. This shows that the change in kinetic energy equals the negative change in potential energy, or that the sum of these two is 0. Therefore, there exists a constant E0 such that the sum of the kinetic and potential energies is equal to E0. Now, because the velocity magnitude squared is the dot product of the velocity with itself, a translational part and a rotational part. When r is perpendicular to v, the magnitude of r cross v is theta prime equals v over r. The direction part, 1/2 mr squared times theta of t squared, can be written as L squared over 2m r squared because angular momentum is conserved. So we can break our original equation of motion down to 3 parts: the translational kinetic energy, the rotational energy, and the potential energy. We've managed to remove theta completely from this differential equation, turning this into a first-order ordinary differential equation. Isolating our r prime of t, we have this expression, and simplifying we get this expression. So here, the angular momentum L will vary with our initial velocity. Later, we'll take the initial velocity to be in between 0 and the square root of gm over r. So far, we have managed to turn our original equation of motion into a first-order ordinary differential equation. The right-hand side of our ODE, the f of r, it is continuous. We can show it's continuous by showing that f of r all squared is continuous. If that's continuous, then so is the original function. In our purpose, that's good enough. By the existence and uniqueness theorem, there should exist an R of t that satisfies this. Now, our ODE doesn't have an analytic solution, but we can shift our goal into solving for R in terms of the angular displacement theta. With the help of ChatGPT, we came up with this solution, where A is 2gm, B is L squared over m squared, and C is 2m over r. The vector solution, so the original r of t, is going to be r of theta times cosine theta in the x direction, r theta times sine of theta in the y direction. Now, to make this expression easier, we can let a over 2b to be a new variable p, and the square root to be a new variable q. So making the substitution, we get a much cleaner version of the distance function with respect to the angle, which is 1 over p plus q cosine of theta. Or, in terms of eccentricity, r of theta equals j over 1 plus e cosine of theta, where j is just 1 over p. For the eccentricity, e equals p over q, it determines the shape of the orbit. If e equals 0, it's a circle. If e is in between 0 and 1, it's an ellipse. If e equals 1, we get a parabola. And when e is greater than 1, we have a hyperbola. From part 2, we've shown that the distance r of t satisfies this ODE. Now setting the derivative to 0 gives us the critical points, as we've learned in Calculus 1. So this turns into a quadratic equation in terms of r, and when we solve it, we get two solutions. We get two roots to be r plus or minus the square root of r squared minus beta, where beta is rl squared over m squared gm. The curvature kappa, which is the magnitude of the derivative of the tangent vector divided by the magnitude of the velocity vector, the magnitude of v cross a divided by the magnitude of v cubed. Now we've seen in part 2 that the acceleration is negative gm over r squared times the unit vector. So we can substitute that into our curvature equation to get this expression. So our v cross a, velocity cross acceleration, becomes r times the change in the angle times gm over r squared, which is gm times the derivative of theta divided by r. The full curvature is shown here. We can now reparameterize this equation in terms of theta to get the equation shown here. Now we know that from part 3 that r equals 1 over p plus q cosine of theta. If our angle is less than 0.5 radians, we can then use the power series expansion, which says that cosine of theta equals 1 minus theta squared over 2 plus theta to the 4th over 4 factorial, and so on. Three-eye Atlas is heading for Jupiter as it leaves the Sun. If we assume that the Sun, 3i, and Jupiter lie in a straight line, we can say that the Sun force points in the negative direction and the Jupiter force points in the positive direction. Let Jupiter's distance from the Sun be fixed. The Sun force then is negative g times m times the mass of the Sun divided by x squared, and the Jupiter force is positive g times the mass of Jupiter times the mass of the asteroid divided by d minus x all squared. The net force causes acceleration, which is, so the net force equals the Sun force plus the Jupiter force, which equals the mass of the asteroid times the acceleration. The acceleration is the second derivative of position, x double prime. So dividing both sides by the mass, we get the initial value problem. X double prime equals minus 2m Sun over x squared plus 2m Jupiter divided by d minus x all squared, with x of 0 being x naught and x prime of 0 being v naught. Solving the second order dE requires numerical integration, So I made a simulation using generalized app generator. Here, I've set x0 and x prime of 0 as user input, and it simulates 3i atlas moving through time with the net force vector. The asteroid reaches the Hill sphere when the net force changes from negative to positive. So this is how Newton calculated the orbits of the planets.
Make sure to give me a like and share it, or give me a comment. The next time you see an asteroid in the sky, you can use my methods to determine whether it'll crash into Earth. If it will, immediately call NASA, and maybe this asteroid will be named after you, like Halley's comet in the 18th century. Sounds cool, right?
That's all for now. See you next time.